Here is a fact that should be impossible. Germany had the better engineers. On problem after problem in the Second World War, German scientists and designers found solutions that were more elegant, more advanced, more technically brilliant than anything the Americans produced. And Germany lost. It lost because a war is not decided by who solves the problem most beautifully. It is decided by who solves it in a way that can be built 10,000 times, shipped across an ocean, fueled, maintained by an ordinary mechanic with a wrench, and replaced faster than the enemy can destroy it. This is a list of 20 specific mechanical problems that both sides faced, the exact same problems, because they were building the same kinds of machines to fight the same war. And it is the story of how, on every single one of them, American engineering found the answer that could be built, while Germany found the answer that was merely correct. Not because the Americans were smarter, often they were not, and where they weren't, this list will say so, but because they understood the one thing that wins industrial wars, which is that the buildable beats the perfect, every time, without exception. 20 problems. Count them down and watch the same pattern repeat until it stops looking like coincidence and starts looking like the reason the war ended the way it did. The early Rolls-Royce Merlin, the engine America would soon build by the tens of thousands at Packard to power the P-51 Mustang, had a flaw that killed pilots. Push the nose down into a dive and negative G-force threw the fuel in the carburetor float chamber the wrong way. The engine starved, then flooded, then cut out for a second and a half, at the exact moment a pilot in a dogfight needed it most. The German fighters, with their fuel-injected Daimler-Benz engines, did not have this problem, and they used it as an escape, bunting into a dive the British and Americans could not follow, their engines choking behind them. The German solution was full fuel injection, sophisticated and expensive and years in the making. The Allied answer came from a woman engineer at the Royal Aircraft Establishment named Beatrice Schilling, a motorcycle racer who had lapped Brooklands at over 100 miles an hour, in an era that barely let women into engineering at all. Her fix was a brass washer with a precisely calculated hole drilled through the center. It cost pennies. She and her team drove from airfield to airfield, fitting it to fighters between sorties, and it was installed across the entire force in months. The Germans solved the problem perfectly. The Allies solved it in time. Hold on to that difference, because it is the whole list. The crankshaft is the most heavily loaded bearing point in any aircraft engine, absorbing the hammer blows of a dozen cylinders firing thousands of times a minute. Germany leaned on rolling element bearings, the balls and rollers whose production was concentrated at Schweinfurt. And that concentration is exactly what made Schweinfurt a target and a vulnerability, the supposed choke point the 8th Air Force bled itself white trying to bomb, 60 B-17s lost in a single October afternoon. The American engine sidestepped the whole thing. It floated its crankshaft on plain bearings, thin steel shells coated with silver, then lead, then a flash of indium to fight the acids in the oil. And here is the beautiful part, the physics the histories skip. The crankshaft never touches the bearing metal at all. As it spins, it drags oil into the narrowing wedge between shaft and shell, and the faster it turns, the higher the pressure climbs, until the oil film itself lifts the shaft and holds it clear, carrying a load of tons on a cushion of liquid thinner than a human hair. The plain bearing takes pounding that would Brunel a ball bearing to death in hours, and it needs not a specialized bearing industry, but the ordinary skills of stamping and plating steel, spread across the whole American economy. There was no Schweinfurt for the American engine, because the bearing that mattered most was made everywhere, out of common metal, by common skills. When a truck or a tank turns, brakes, or corners, its wheels are pushed sideways as well as pressed down, a mix of radial and thrust load that an ordinary ball bearing handles poorly. Germany relied on more complex arrangements of separate bearings for the separate loads. America had Timken, a company founded by a German immigrant carriage maker named Henry Timken, whose tapered roller bearing took both loads at once on a single cone of rollers set at an angle. America built them in numbers that put them into every truck axle, every tank hub, every machine tool spindle the war demanded. The immigrants' angled roller was one of the small, invisible things that let the entire American supply chain roll mile after mile without ceasing. Every engine, every transmission, every gun turret depends on gears cut to tolerances measured in 10,000ths of an inch, and cutting them fast was a central problem of the war. Germany cut its gears with superb craft, skilled machinists at hobbing machines producing beautiful gears, slowly, one careful pass at a time. America attacked the problem with the broaching machine, a tool that pushed a long bar studded with progressively larger cutting teeth straight through the metal in a single powerful stroke, each tooth removing a little more than the last, so a finished gear profile appeared in seconds where the German method took many minutes. It was not more precise than the German craftsman. It was faster by an order of magnitude, and it needed no craftsman at all. German tank factory managers, according to accounts from the period, feared American broaching machines more than they feared Sherman tanks, because the broach was the thing that let America turn out gears, and therefore transmissions and tanks, and aircraft, at a rate Germany's slower methods could never approach. To machine armor plate and gun barrels and hardened engine parts, you need cutting tools harder than the steel they cut, holding their edge at the glowing temperatures fast machining generates. Germany had excellent high-speed tool steels, some of the best in the world. America, through General Electric and Carbolloy, mastered cemented tungsten carbide, tool tips of carbide particles bonded in a metal matrix that stayed hard at temperatures which would have softened tool steel, cutting faster and lasting far longer. And the same hard, dense carbide, formed into the core of an armor-piercing shell, cracked the face-hardened steel of a Panzer that ordinary shot bounced off. When tungsten grew scarce, American engineers stretched it with substitutes and conserved it where it mattered, so neither the cutting nor the armor-piercing ever stopped. The tool that cuts the steel is as decisive as the steel, because a factory whose tools fail is a factory that stops. A spark plug no longer than a thumb has to survive inside a combustion chamber firing 50 times a second at temperatures approaching 2,000 degrees Fahrenheit while the metal around it glows. Fouled or cracked plugs could ground an engine, and the Wright R3350 radio that powered the B-29 was murder on them, its rear cylinders fouling so fast that on the early engines, the plugs were pulled and replaced every 25 hours. The problem was the ceramic insulator, which had to conduct heat at exactly the right rate, survive the thermal shock of 50 firing cycles a second, and insulate tens of thousands of volts all at once. The answer was the transition from fragile layered mica insulators to sintered aluminum oxide ceramics, refined by Champion, that took the shock and the lead fouling and kept firing. Invisible engineering, thrown away by the thousand, logged in and out by ground crews on Pacific Islands. The bombers did not fly without it. Germany actually started ahead here. German tanks pioneered radio coordination in the 1930s, and it was a major reason their early blitzkrieg worked, every tank hearing its commander. But Germany stayed with amplitude modulation, AM, whose signal drowned in the electrical noise of a tank's own engine and ignition and generator, so that a commander in a moving vehicle often heard mostly static. America, through Motorola, a former University of Connecticut professor named Daniel Noble, and a Polish refugee engineer named Hendrik Magnuski, who had fled the German invasion of his own country, put frequency modulation, FM, into its tank and infantry radios. FM, by its very physics, ignores amplitude noise and reads only the frequency, so the interference simply falls away and the voice comes through clean. The American tank commander gave a clear order that every tank in his company heard through the static. The American infantry carried the SCR-300 walkie-talkie that coordinated the squads. The side that pioneered tank radio was outcommunicated in the end by the side that perfected it. America had never built a dedicated tank engine and had no time to design one, so it solved the problem 5 ways at once. Germany built purpose-designed Maybach tank engines, beautifully engineered from the first drawing, and built about 6,000 Panthers across the whole war. America improvised on a scale that beggars belief.
It put an aircraft radio, the Continental R975, in the Sherman when that was what it had, and built over 50,000 of them. It bolted two General Motors bus diesels together side by side into the GM 6046, each engine separately clutchable, so a crew that took a hit could disconnect the dead half and limp home on the other. It cut 4 cylinders off a failed aircraft V-12 to make the Ford GAA, the largest gasoline V8 ever mass-produced, 500 horsepower and so overbuilt that post-war racers pulled 2,000 from it. And when it still needed more, Chrysler bolted 5 ordinary passenger car engines together around essential gear into a 30-cylinder monster, the A57 Multibank, 30 spark plugs and 5 carburetors that ran reliably and could keep the tank moving with 2 of its 5 engines shot dead. None was elegant. Every one was buildable, now from parts America already made by the 100,000. America built nearly 50,000 Shermans. Germany had the single better engine. America had more engines of more kinds than Germany could imagine. Every German tank used a manual gearbox, demanding a trained driver working a heavy clutch and a difficult shift while bouncing across a battlefield. America, through Cadillac, put automatic transmissions into its light tanks, the same Hydra-Matic developed to pamper luxury car buyers, so a farm boy who had never driven anything but a tractor could learn to drive an M5 Stewart competently in an hour instead of weeks. And through Buick, it built the M18 Hellcat tank destroyer around a Torque-Matic torque converter transmission that multiplied the engine's torque nearly 5-to-1 through a churning wedge of oil, helping make the Hellcat the fastest tracked vehicle of the war at 55 miles an hour, faster than the M1 Abrams that came 40 years later. The luxury car technology of smoothness became a military weapon because a tank that is easy to drive is a tank that quickly trained crews can actually fight. The same Merlin that made about 1,000 horsepower on old 87-octane fuel made over 1,300 on the 100-octane fuel America's oil industry learned to produce through catalytic cracking. First, the Houdry process, invented by a Frenchman named Eugene Houdry, who fled to America and refused to sell his process to Germany, and then fluid catalytic cracking, developed by a team of American engineers. Octane is a measure of how hard you can squeeze and boost a fuel before it detonates on its own and tears the engine apart. Higher octane let the engine run higher boost without detonating, and that boost was raw power, the margin of speed and climb that won dogfights over the Channel. Germany, cut off from natural petroleum, made synthetic fuel through Fischer-Tropsch and hydrogenation, a genuine chemical triumph that kept the Reich fighting for years. But it could never make enough, and its aviation fuel was generally lower octane. The engines might be equally well designed. The Allied engine drank a better fuel and drank as much of it as it wanted, and the German engine did neither. An engine coolant that froze would crack a cylinder block and kill a tank as surely as an anti-tank round through the hull. America produced ethylene glycol, sold as Prestone, by the hundreds of thousands of tons, enough to protect every liquid-cooled vehicle on every front through every winter. Germany's supply of proper antifreeze was a small fraction of that, and German vehicles suffered accordingly in the Russian cold, where crews sometimes had to keep engines running around the clock or drain them entirely just to keep them from freezing solid. The unglamorous fluid in the radiator was the difference between an engine that started on a frozen morning and an engine cracked beyond repair. A single bullet through an ordinary fuel tank meant a stream of fuel, a spark, and fire in the air killed crews in seconds. America lined its aircraft fuel tanks with layers of vulcanized and raw rubber that swelled the instant they were soaked in leaking fuel, closing a bullet hole almost as fast as it was punched. The technology is credited with saving thousands of aircrew who would otherwise have burned. Germany used self-sealing tanks too, but the Allied rubber supply, natural and synthetic together, was deeper, and the protection was applied more widely and more consistently across the whole force. Japan's conquest of Southeast Asia cut America off from 90% of its natural rubber almost overnight, and Germany had never had reliable access at all. Both built synthetic rubber industries. Germany's Buna rubber, made by the chemical combine IG Farben, was a real achievement and came earlier. But America, through a crash program that built 51 synthetic rubber plants in about 2 years, outproduced the entire German synthetic rubber industry many times over, turning a near-fatal strategic vulnerability into a flood of tires and gaskets and hoses and seals. Germany invented much of the chemistry. America built the overwhelming scale. That sentence, in one form or another, is the whole war. The gyroscope was the spinning heart of the bomb sight, the autopilot, and the gun stabilizer, demanding rotors balanced and bearings finished to tolerances few industries could hold. America turned to its watch and instrument makers, companies that already knew how to build tiny, precise mechanisms and produced gyroscopes and Norden bomb sights by the hundreds of thousands. And it solved a related problem the Germans largely did not: gun stabilization, putting a gyroscope in the Sherman that held the gun roughly on target while the tank moved over rough ground, so American tanks could fire on the move, while German tanks generally had to halt to shoot. The stabilizer was crude, and many crews switched it off or distrusted it, but it worked well enough to matter, and it pointed toward a future of fire-on-the-move gunnery the Germans had not reached. The proximity fuse was one of the most closely guarded solutions of the entire war, ranked in secrecy just below the atomic bomb. The problem was building a tiny radio transmitter and receiver small enough to fit in the nose of an artillery shell, tough enough to survive the shock of firing, a force of some 20,000 times gravity that would shatter any ordinary electronics, and clever enough to sense by the echo of its own signal when it was near the target and detonate there. A gunner no longer had to score a direct hit or guess the fuse timing. The shell simply burst when it came close. It made anti-aircraft fires several times more effective, broke the German V-1 flying bomb offensive over England, and later, against ground troops at the Bulge, burst shells in the air above the enemy with devastating effect. It required ruggedized electronics, vacuum tubes that could be fired from a cannon and keep working, produced in the millions, exactly the mass precision electronics that America could manufacture, and Germany, whatever its scientists knew, could not match at scale. Keeping hundreds of thousands of radios each locked precisely on its assigned channel depended on precisely cut slivers of natural quartz that vibrated at an exact frequency. America needed tens of millions of them. It imported the raw quartz from Brazil, built an industry to cut and grind and finish some 30 million frequency control crystals, and in doing so, underwrote the entire American radio effort, the FM tank radios and the walkie-talkies and the aircraft and ship sets alike. Without the crystal, there is no channel. Without the channel, there is no coordinated net. America went from a standing start to 30 million crystals in a few years. Aluminum and magnesium are the light metals that make aircraft possible at all, and both are won from their ores by pouring vast quantities of electricity through them. America, through Alcoa and Dow, built the largest aluminum smelters on Earth and extracted magnesium directly from seawater, from the endless supply of the ocean, on a scale that flooded the aircraft factories with light metal. Germany was resource-constrained and had to ration and substitute at every turn, stretching its light metal supply thin. An airframe is only as available as the metal it is made from, and America simply had more metal, produced with more electricity than Germany could bring to bear. Moving supplies across an open beach under fire was a problem America answered with the Detroit diesel that powered the Higgins boats and with the DUKW, the amphibious truck designed in about 38 days by a yacht designer named Rod Stevens who had won the America's Cup. It was a 6-wheeled truck wrapped in a boat hull that could be loaded at a ship, swim to the beach under its own propeller, and drive inland without ever stopping at the waterline. Germany never faced quite the same problem of supplying armies across oceans, but the deeper point stands. America treated logistics itself as an engineering problem to be solved with purpose-built machines, and then built over 21,000 swimming trucks to solve it, because the beach was a bottleneck and the DUKW dissolved the bottleneck. A tank whose engine failed was a dead machine unless you could repair it fast, and here the two philosophies collided head-on. German equipment was often superior in design and hand-fitted in manufacture, its parts finished by skilled workers to match one particular machine, so that replacing a part meant fitting a new one all over again, slow work needing a skilled hand. American equipment was built so that any part dropped into any machine. A Sherman's entire engine could be unbolted and a fresh power pack dropped in and running in a few hours by ordinary mechanics, using quick disconnect couplings designed for exactly that. The German tank that broke down behind the lines waited for a craftsman. The American tank that broke down was back in the fight by afternoon. Reliability you can repair beats performance you cannot. The deepest thing American engineering solved, the thing that made all 19 others possible, was interchangeable mass production itself. The whole philosophy of making complex machines out of standardized parts so precise and so consistent that any one fit any machine without hand-fitting, so the machines could be assembled by unskilled labor in enormous quantity, and so a factory that had never built a weapon, an armories of the 19th century, or a washing machine plant or a car body stamping shop could be handed the drawings and start turning out finished weapons within months. This was not one invention on one day. It was a philosophy America had been building since the armories of the 19th century, and it was the master solution from which every other one on this list flowed. The broaching machine, the carbide tool, the plain bearing made everywhere, the 5 improvised tank engines, the automatic transmission that let farm boys drive tanks, all of them are expressions of the same commitment, the buildable over the perfect, the many over the exquisite. Germany kept solving, brilliantly, the problem of how to make the best possible machine. America kept solving the different problem of how to make the most possible machines that were good enough. And in a war that lasted 6 years and spanned every ocean and consumed materiel faster than any conflict in history, good enough multiplied by 100,000 and delivered on time and easy to fix beat perfect and rare and late every single time. That is the pattern across all 20 and 100 more that would not fit. Germany was frequently ahead in the laboratory and behind in the mud. Ahead on the single perfect example rolled out for the general, and hopelessly behind on the 10,000th unit the war actually needed. And honest history has to say plainly that the German engineers were not defeated because they were wrong. They were among the best in the world, and much of what they built was superior. They were defeated because being right in a war of industrial attrition is not the same as being able to build it, ship it, fuel it, maintain it, and replace it faster than the enemy can destroy it. Look around, and most of these solutions are still here. Timken still makes tapered rollers. Champion still makes spark plugs. The plain bearing still floats the crankshaft in the engine of your car on its film of oil. The automatic transmission Cadillac put in a tank is in nearly every car on the road. The interchangeable parts philosophy is simply how everything is made now, everywhere, so completely that we have forgotten it was ever a question. Every one of these 20 was a bet on a single principle, that the solution you can build beats the solution that is merely correct. Germany chased the perfect, America chose the buildable, and the buildable won the war.